since the time is not much, and I see lots of younger audience and who may not be from high energy physics, so I will give a very broad overview without going into too much of technical details. So the experts in the audience, kindly please excuse me for that. So this is the brief outline of my talk. I will give a very brief introduction to the subject and some amount of history of the neutrinos, and what are the sources of neutrinos, and how the discovery of neutrino oscillations happened, and what are the unsolved mysteries that we still have and people are still working on, so that the people who are interested may actually pursue it for their higher studies. And more importantly, I will also touch upon what India is playing, what role India has been playing for last 5-6 decades for neutrino physics. And then I will conclude. And so this is just a cartoon showing that length scales that we typically talk about when we discuss physics, because we would like to use our physics principles to describe phenomena occurring at all these possible length scales that we are aware of. For example, starting from the size of the universe, which is extremely huge in size, to the size of elementary particles like quarks, electrons, and neutrinos, which are, for all practical purposes, which are of zero size. So we have to explain everything using the same common principle, and sometimes it turns out that we describe at the most fundamental scale, or the lowest possible length scale, also somehow affects the physics at a very large scale. So neutrino is one example. I will just touch upon those things if I have time. So yesterday, Professor Paulos already gave a very nice introduction to the elementary particles. So you all know that there are all these sets of different particles that we know. So some are called quarks, which are basically the building blocks of protons and neutrons, which you know very well. And there are electrons and neutrinos, and similarly the other cousins, which are like slightly heavier than electron, which are called muon and tau. And on top of these fermions, we also have some bosons with spin 0 as well as spin 1. And the photon is the most familiar example. And there are many others also, which are called W boson, G boson, which are actually responsible for weak nuclear force. There's something called gluon, which is responsible for the strong nuclear force. And the most interesting, or the latest development, is the Higgs boson into the picture, which was discovered in 2012. Okay, and that has a mass of around 126 times the mass of the proton. Okay. And on top of these particles, you also know that there are 4 different forces, and which I have already mentioned, and they have different strengths. So strong and weak nuclear forces, they are very short range force. We don't see them in our daily life because they operate only inside the nucleus or inside the protons. Electromagnetic and gravity, we encounter them every day in our life, and they are infinite range forces. There's a cross mark, as you can see, on the gravity, because we do not have a quantum theory of gravity. So that's why we do not know how gravity will behave if we want to go to the smallest possible distances. So that's why all the standard model of particle physics, they try to describe only the first 3 interactions: strong, electromagnetic, and weak. And gravity, so far, we don't have a good understanding at the most fundamental level. So this is a brief history of neutrinos. As you can see that it was actually hypothesized, or actually proposed as by Pauli, the same Pauli of Pauli's exclusion principle. And it took some time to actually experimentally discover it. And you can see that the field evolved quite a lot from 1930s to the present day, almost like 90 years. Okay, and still we need to understand many more things about neutrinos. So to a first approximation, neutrinos weigh nothing. So neutrinos are basically the lightest fundamental fermion we know of. And initially people actually thought that it is massless. Okay, and it does not interact with anything to a first approximation because it does not have electromagnetic charge. Okay, then why somebody actually predicted their existence in 1930s when it was not even experimentally discovered? Okay. But in reality, right now, we know that neutrinos are not exactly massless. They have a very, very tiny mass compared to the known particles like electrons, muons, protons, neutrons, and all. And it interacts very, very weakly with ordinary matter, just because it doesn't have electromagnetic charge. Okay, so that's what makes it very difficult to detect neutrinos experimentally. And on the other hand, the way we see ordinary matter is that it actually interacts with the electrons due to their electromagnetic interaction. So that makes it very difficult to see an electron because it can bend in a magnetic field. It can interact with your atoms due to electromagnetic interaction. So, and it can emit some light or it can deflect some light. But neutrinos, on the other hand, cannot do that because it doesn't have a charge. So how the proposal came? The proposal came because there was some problem in beta decay. Okay, so there was a problem of the conservation of laws of energy, which was found to be violated in the beta decay. So earlier, what people thought is that a beta decay is a process where a heavier nucleus, unstable nucleus, decays into a more stable nucleus and an electron, and the electron is called a beta particle. Okay. So people initially thought that it's a two-body process. So at the fundamental level, you can think of it as a neutron going into a proton and an electron. So it conserves charge. It is also allowed by mass energy conservation. But there was a problem which people saw. I will talk about that. Another problem is the spin. For example, neutron is a spin half particle, proton is a spin half particle, electron is a spin half particle. So if you have a process where neutron goes into proton plus electron, a spin half particle cannot go into two spin half particle because half plus half will not give you half. Half plus half will give you either 1 or 0. So that was another problem. So there are two problems. One is conservation of spin and one is conservation of energy also. So I'll talk about it. So if it is a two-body process, for example, a nucleus at rest decaying into another daughter nucleus and an electron. So it's a very simple kinematics you can do using the Newtonian conservation. So you expect that all the energy to be carried away by the electron only. Okay. So if you know the mass of the daughter nucleus and the parent nucleus, so the energy carried away by the electron is basically the mass difference. So you know that only all the electrons coming out from the particular beta decay will have only one value of kinetic energy. But what people have observed is that electrons carry a continuous spectrum of energy. As you can see in the blue curve here, it gives a continuous spectrum, okay, not just the red one which is expected. So that led to people think that, okay, there is some violation of conservation of energy because you calculated this red portion using the conservation of energy, but what experiments give is that the blue line, okay. So there was a problem in there, okay. So this is a simple calculation of kinematics. You see that the kinetic energy, TE, carried by the electron is basically the mass difference, okay, the Q value of the nuclear reaction, okay. So this is fixed because your initial nucleus and the final nucleus are fixed, okay, and both are very heavy and they are at rest almost. Now, why the existence of neutrino was proposed? So the Pauli proposed because there were problems. So Pauli thought that it may not be a two-body decay, it may be a three-body decay. So there is one more particle in the final state. And it's a very simple kinematics using Newtonian mechanics you can do that if you try to solve the energy carried away by the electron, considering three particles in the final state, you will find that it is not a fixed number, okay? So it can take many possible values because there are infinite ways to balance the momentum of three particles, okay? But in case of two particles in the final, so there's only one way. They will go equal and opposite to each other, okay? So that actually solved that problem. And what Pauli also proposed that the neutrinos should have a spin half because that will again solve the spin problem that I talked about because half plus half can give you half. And it also explains the continuous spectrum. So that actually, but that was a hypothesis in 1930s because it was not experimentally observed. And Pauli also regret that he proposed something which cannot be detected because it is chargeless and it is almost massless. Okay. And in 1934, Fermi, the same Fermi of Fermi-Dirac statistics. So Fermi actually proposed the complete theory of beta decay. What do I mean by complete theory of beta decay? So you have to propose a theory which will actually predict the lifetime of a beta decay process. Okay. So Pauli proposed. Fermi did that using that what is called Fermi's golden rule, which you might have seen in the quantum mechanics, the perturbation theory of quantum mechanics. So it's a very simple formula which you can use by taking the initial quantum state and the final quantum state and then taking the interaction Hamiltonian, and that should predict the lifetime of the process or the half-life of the process. Okay, so Fermi did that, and but that also had some issues because it was very preliminary. So it took some 20 years or so for others to actually develop a complete detailed model to actually predict the beta decay lifetime to a very general extent. So after Pauli's proposal, beta decay came to be known as a three-body process where parent nucleus goes to daughter nucleus plus electron and an anti-neutrino. Okay? And the same process, like a neutron going to proton plus electron plus antineutrino, you can actually rearrange them in several possible ways. And there are different avatars of the same process, basically. At the fundamental level, they are same processes, but they play very different roles when we try to detect neutrinos or we try to create neutrinos. Okay. And neutrinos come in 3 different flavors. Okay, and it's not just the electron type. You can see the subscript here. This is if it is E, that means it actually produced in association with an electron. So if I replace the E by mu, it will be produced with a muon. So if I replace the subscript by tau, it will be produced with a tau. Okay, so neutrinos come in 3 different flavors, just like the charged fermions, or like the electrons come with 3 different flavors, like electron, muon, and tau. Okay. So how to detect neutrinos? So using the Fermi's theory, people actually made a calculation that neutrinos, if a neutrino travels through some kind of solid matter, at what point it will actually interact with solid matter and produce something else, which you can actually see in ordinary microscope or your instruments. Okay, so they found that in a typical solid, neutrinos will have to travel for 100 trillion kilometers to actually interact with a normal atom and produce something else. Okay, so 100 trillion kilometers is like a practically impossible distance to conduct any experiments. So even if you take a very dense material like lead, even there, the mean free path, or the path the neutrinos will travel before interacting with a lead atom, will be more than a light year. Light year is basically the distance traveled by light in 1 year. Okay, so that all these things are impractical. So then what people thought is that we need some very special type of detector for a neutrino. And what is the role people play? All these rate of interaction are basically probability. Okay, so for one neutrino, the probability is very small. But since probabilities are multiplicative, you can try to design an experiment where you have a huge number of neutrinos. So since this is the modern view. So follows hello, am I audible?
Yes, sir.
So sorry, I mean, it got disconnected. So I mean, which slide you saw last? Can you tell me? I'm on slide 18 now. There's a beta decay modern view.
Let me ask if anyone is.
I mean, did I got disconnected in between?
Yes, you got disconnected, but
in the participants, so I think you can more or less continue.
Okay, fine. Thank you. Okay, all right. So this is a modern view of the beta decay. As you can see, using quantum field theory, we think about any fundamental force as arising to the mediation of some particles. So here you can see W bosons. Yes, hello.
So your screen is not visible to us.
Oh, okay, it got disconnected. Okay, sorry. Can you see now?
Yes.
Yeah. Can you see now?
Yeah. Thank you, sir.
Okay. Yeah. So this is the modern view of beta decay in terms of quantum field theory, where you have all the possible interactions like weak nuclear force arising as due to the mediation of this W bosons, which are like some kind of mediating particles of spin 1. And this modern view was basically known as the standard model of particle physics, which was put forward by Glasgow, Salam, and Weinberg, who also got Nobel Prize in 1979. Now, discovery of neutrinos. So people have to detect some. People have to design some experiments where you have a source of neutrinos which has a very huge flux, because that will increase the probability of detection. And you also should have a very huge detector, because as you have seen that the mean free path of neutrinos are very long. So your detector should be large and your source of neutrinos should have a huge flux. So that is the principle one has to follow. So Cowan and Rains in 1956, they tried to produce neutrino flux using a nuclear reactor. Nuclear reactor also has some kind of beta decays and other processes which emit lots of neutrinos. So they made sure that there is a huge flux of them. And they used those flux of neutrinos from a nuclear reactor and actually discovered neutrinos from these processes, that neutrinos will actually hit the atoms and in a tank of water, and it will emit neutrons and positrons. So this is one of the beta decay processes I talked about, where neutrino hit a proton and it will create a neutron and a positron. Okay, so the positron is basically the antiparticle of electron, which you can see because it has electromagnetic charge. Okay, so using that kind of approach, people actually discovered the electron type neutrino. Then a muon type neutrino was actually discovered in 1962, and the third type of neutrino, which is tau neutrino, was discovered in 2000. So it took a long time. So in 1930 it was proposed, 1956 was the first discovery, then 62, then 2000. So it's extremely difficult job, but people did that over a span of like a few decades. Okay. Now coming to neutrino sources. So what are the sources that you can think of? Am I audible? Hello?
Yes, sir. Yes, sir.
Okay. Yeah, there's lots of fluctuations in the okay, so the neutrino sources, as you can see in this cartoon, there are many sources of neutrinos. One obvious one is the sun. From the sun, we are getting lots of neutrinos every second. And there can be atmospheric neutrinos, which I will touch upon. Then there can be neutrinos from reactors. There can be neutrinos from accelerators. There can be neutrinos from different sources inside the galaxy, like other stars, supernovae, and so on. And there can be neutrinos coming from outside the galaxy also. And people have indeed discovered neutrinos coming from a source which is far away from our Milky Way galaxy. And at the bottom, you can see that there are sources from Big Bang also. Okay. And this plot, in the y-axis, you have cross-section, which is the rate of interaction, and as a function of energy. As you can see, that if you have more energy, more neutrino energy, there's a more probability of detecting it. Okay, so that is what we always expect. So the neutrinos from sun, so sun produces 10 to the power 38 neutrinos per second. Okay, so that one can estimate because we know in how many neutrinos are produced in each proton-proton cycle, and from the power emitted by sun, one can estimate how many proton-proton cycles are happening. So from that, one can estimate how many neutrinos you expect. Okay. So then Davis and Bacall, they actually designed an experiment to detect neutrinos from sun, and they actually did that in 1968. So they used chlorine or the cleaning fluid as a detector for the detection of solar neutrinos. And it was an extremely difficult job. Okay, so he did that in 1968. I will skip the details. So this was a very latest update. You can see that June 2020. So people actually found the neutrinos. People actually experimentally detected neutrinos coming from one of the very rarest fusion processes inside the sun. Okay, so that actually led to a confirmation of our understanding about how actually nuclear fusion is happening inside the sun. So I will skip the details for that. Atmospheric neutrinos, so the cosmic rays. So cosmic rays are basically charged particles, mostly protons. They're coming from very far away sources, which we don't know very well. So what they will do, so they will hit the air molecules in our atmosphere, and it will produce lots of other particles. Okay, so out of those lots of other particles, there will be neutrinos also. So we expect some muon type of neutrinos from the atmosphere. Okay, they are generated by the cosmic rays. There can be neutrinos from supernovae. Supernovae is basically the explosion of a star once it runs out of its fuel, and that emits actually lots of neutrinos. You can see 90% of the gravitational binding energy of a star, which is actually blowing up, is actually emitted in the terms of neutrinos. And people actually observed those neutrinos from a particular supernovae in Large Magellanic Cloud in 1987, and which actually led to the start of a neutrino astronomy, and which has evolved to a very big field now. So this is just a picture of a neutrino detector. As you can see, as I told earlier, that neutrino detector has to be very, very large because neutrino has a very long mean free path. So this is a water Cherenkov detector in Japan, Kamioka. And this cartoon actually tells you how actually they are detected. So neutrino will come from somewhere. It will hit your water molecule, and it will eject a charged particle. And the charged particle will actually move with a speed faster than the speed of light in that particular medium, not faster than the speed of light in vacuum. So in a medium, massive particle can actually travel with a speed faster than the speed of light in that medium. So then it will emit something called Cherenkov light, and light can be detected very easily. So that is the working principle of all these water Cherenkov detectors. So this is from Super Kamiokande in Japan, and this is similar from the Sadhguru Neutrino Observatory. They looked for neutrinos coming from the sun. Super Kamiokande looked at neutrinos coming from the atmosphere, and they both led to the Nobel Prize in 2015. So neutrino detectors are pretty big, actually. So that is the basic thing. So neutrinos from Big Bang. So you have already heard about Big Bang yesterday. So neutrinos can come from Big Bang also. So this diagram you have seen yesterday, So neutrinos can come from Big Bang. So what happens that the neutrinos are interacting. So as you go back and back into the early, hello?
Yeah, sorry
hello?
to interrupt. 5 more minutes to wind up, please.
5 minutes? Okay, okay, fine.
5 more minutes to wind up, sir.
Okay, okay, I'll do that.
Yes.
Okay, fine. Okay, so this diagram you have already seen. So neutrinos actually come from a very long time during the Big Bang. So they can be actually detected. So you can actually make this calculation. You can find that around 350 neutrinos are there per centimeter cube in the present universe. So this makes neutrinos the second most abundant particle in the universe after photon. Okay. And neutrinos actually are coming from just 1 second after the Big Bang. So after the 1 second, they are free streaming because their rate of interaction falls below the rate of expansion of the universe. So they don't interact anymore and they keep moving. So they can give us a picture of our universe as young as 1 second. So yesterday you heard that the cosmic microwave background gives us a picture of our universe when it was 380,000 years old. So if we can detect the neutrinos from the Big Bang, we will get a picture of our universe as young as 1 second. So that is very nice. So, but people have not detected it because they are very low energy. So it is extremely hard to detect the neutrinos coming from Big Bang. So people are working on that. So let me actually skip these things. So I'll come to the neutrino oscillation. So why neutrino oscillation was proposed? Proposed because we expect 10 to the power 38 neutrinos from the sun, for example, okay, per second. But what we find is that, for example, all the neutrinos in the sun should be of electron type because this is a typical beta decay where electrons are emitted. But we are not getting the exact number of electron type neutrinos in our detector. So that led people to think that maybe on the way neutrinos are actually changing its flavor to muon type or tau type. So this is a very simple quantum mechanical exercise. For example, if your quantum state is not a stationary state, it is a mixture of some stationary states. So if you do the time evolution, so you will find that that mixture of different states will actually evolve with time and actually change it to a different field. Okay, so that is what is happening in neutrino oscillation. This is a simple two-flavor quantum mechanical calculation. So we can calculate that what is the probability of one type of neutrino going into another type of neutrinos, and that one can actually plot. And as you can see that the neutrino probability as a function of the distance of travel or the energy of neutrinos. So neutrinos can change its flavor from one to another, and that has been experimentally observed. And that actually led to the Nobel Prize in 2015 to Kazita and McDonald. And they actually led the two experiments at Kamiokande and SNO. Okay, I'll skip. So this is very important from the young audience who want to take up neutrino physics as their research, maybe in future. So that's, we do not know where the neutrino mass originates. We do not know whether which one is heavier and which one is lighter. So there are two possibilities. They are called normal and inverted. We do not know CP violating phase. Hello? Hello? Yeah, did somebody say something? Hello, can you hear me? Hello?
Yes, sir, we are hearing, sir.
Okay.
Yes, sir.
Okay.
You're audible.
So,
Go ahead.
yeah. Okay. So we also do not know whether neutrinos are Dirac or Majorana. Basically, neutrinos are its own antiparticle because it is chargeless. So there is a possibility that it can be its own antiparticle, but we do not know it yet, and we do not know if there can be some more neutrinos apart from just three. Okay. So these are the unknowns that we have. How neutrinos acquire mass. So we know that all fundamental particles acquire mass from the Higgs boson, but it is not clear whether neutrinos get mass from the same Higgs boson that I have talked about, which has been experimentally observed. So people are still working on that. There are many ways to generate neutrino mass. The one is called seesaw mechanism. This question I would like to ask that I'd like to mention is that because you have already heard about dark matter. So one question is that can neutrinos be dark matter? Because neutrino is stable, neutrino doesn't have charge. Can neutrinos be dark matter in the universe? Many people actually ask that, but a simple calculation shows that no, neutrinos cannot be dark matter. Neutrinos give us a very small component of our energy budget. And neutrinos can play a role in the matter-antimatter asymmetry, which Paul has also talked about. So that is the one interesting option because neutrinos sector can have very large CP violation. So this article, as you can see, this is from Nature, in April 2020. So this experiment, Day2 said that they have seen some large CP violation in the neutrino sector. So that could be the lead to an answer that why we have more matter in the universe compared to antimatter. Okay. I will skip that. So India's role, last two slides. So India has people in India, for example, in TIFR, they have started working on neutrino experiment as long as back like 1965. So they actually did some experiment in the Kolar gold mine, which is now closed. And they actually discovered the first atmospheric muon type neutrinos. And this was one of the first in the world, and at the same time as one experiment in South Africa. So many people actually don't know about this very early development in the field, especially in our country. So you can look at these perspectives of experimental neutrino physics in India by P.S. Narasimham for the details. We also have our own observatory called India-based Neutrino Observatory, which is proposed to be built, and they have already done their detector part and all the simulations and the design. And so you can look at this website for the details. So this is my own research interest. I will skip that part because I don't have time. Conclusion, so neutrino physics has emerged or evolved substantially in the last 8-9 decades or so. So the understanding of neutrinos can reveal many secrets of the nature, covering wide areas of particle physics, cosmology, astrophysics, and so on. And with experimental frontiers getting incredibly precise and sensitive, many new things in neutrinos will be discovered very soon. And with India starting its own observatory, there lies exciting days ahead for students willing to work in this field. So I will stop here. Thank you.
Thank you, sir. Thank you for nice presentation and giving us some area for our young researchers. Since we are again short of time, straightly we'll go for question hour, and we'll take only one question, sir. So from this class, anyone can ask one question only. We'll allow one person to ask question. Hello.
Hello, sir.
There are no questions. Oh, yes.
Excuse me, sir.
Hello.
Excuse me, sir.
Yeah,
Yes.
other question.
Yes, there is one question from Anmol Subba.
Yes.
He's asking that we know that quarks combine to form bigger particles like proton and neutron.
Yes.
And why doesn't other particles like, for say, neutrino combine and form bigger particles?
Okay. Yeah, that is basically because of the fact that quarks have very strong interactions, so they can form bound states very easily. And quarks also have a very interesting property that they cannot exist freely. So quarks cannot exist freely because something called asymptotic freedom. So quarks are always confined, but that property is not applicable to other fundamental particles which do not have a strong interaction. So that's why other particles do not form that kind of bound state. I mean, you can think about Cooper pairs in, superconductor, which is formed out of electrons, but those are like not fundamental particles. They are like some kind of effective bound states in condensed matter system. But fundamentally, only the quarks can do that. I hope that is clear.
Thank you, sir.
Okay.
Okay, thank you, sir. Thank you.
Thank you.
Rest, if the participants have a question, they can, I suppose, ask directly to Dr. Devas. He's an assistant professor in the Department of Chemical Science, Sikkim University. His area of specialization is coordination and organometallic chemical, homogeneous and heterogeneous catalyst, and so on. He has several awards, that is one or two of them to mention. DST Inspire Faculty Award 2015, UGC Research Fellowship in Science and Meritorious Students 2009. And also he has 24 years in his credit. Make presentation on the topic framework as functional materials. Just to remind him that we are running short of time. There 25 minutes so that we finish on time.
Okay.
Over to Anand.
Thank you, Father Donas. It was nice to see you after a long time. It's been long. We haven't met actually.
Yes, yes.
Thank you very much. Thank you, host
Right, right.
Amit and all for giving me this opportunity for this talk. I would like to share my screen. Uh,
Sir,
okay. Just give me a second. Okay. Yeah, I hope it's visible now, right?
yes, sir. Yes, sir.
Yeah, I'll be talking about metal organic framework as functional materials today. So metal organic framework has come up as a new generation porous material, which are highly been sorted out in these days. Especially the last 2 decades have been extensively focused on development of this material. So among diverse material, this metal organic framework, we generally call it as MOF, and they are rapidly emerging. So without losing any time, I would straight away like to go into the details. The talk today will be completely focused on especially the PG and the UG students. So it will not be that advanced. So it would more be like tutorials on metal organic framework, especially some introduction, its synthesis, its properties, and a little bit about the kind of work we are doing in our lab. So to start with, so metal organic framework actually, it's almost similar like a metal complex, but because it attains a different kinds of properties, so they have been classified into a different class of hybrid materials, and they generally contains metals, metal ions. It can be transition metal ions, it can be a heavy metal ions, and ligands, definitely ligands, organic ligands. So, and they can be synthesized in way different ways, and they can form 1-dimensional, 2-dimensional, or 3-dimensional arrays, which eventually will give rise to a very robust structures that has lots of different kinds of properties, and very fascinating and robust system. So technically, to define a metal organic framework, we define it by saying that it is a coordination network. So they are highly coordinated and with organic ligands, definitely, but contains potential voids. Now this potential voids is very important because all these materials generally are very porous, and this porous uh, places, this pores are most of the times occupied by different solvents that can actually be taken out, and they can be made highly porous. So to start with, I'll directly go into the synthesis part. So there are several ways to synthesize a metal organic framework in your lab. So it's not very difficult to synthesize, and there are several ways. So to make my talk a little bit simple on synthesis, I've just taken a very specific examples. HKUST1, it's a one of the pioneer metal organic framework. And remember one thing, naming of metal organic framework is been named in a very unique way. So generally what people do is they name metal organic framework with respect to their respective universities. So for example, in this case, HKUST1 means Hong Kong University of Science and Technology. So in any way, if we prepare a new metal organic framework, we generally name them as SKU1, Sikkim University 1, Sikkim University 2, and so on and so forth. So this is, I've taken an example for HKUST1. So it's a copper. So it has a copper ion, copper salt, and a ligand. So this is benzene tricarboxylic acid, which gives a typical polymeric structure, Cu2 BTC3N. So it is a polymeric structure. So this is just an empirical formula. So there are several ways. You can synthesize it with solvothermal way, you get the same product. You can do it with direct precipitation where you just add two salts and you immediately get your product, or you can even make it through ultrasonication. You can even use microwave, or you can even do it in electrochemical way. So the synthetic part is not very difficult, but the overall process to identify it and to isolate it and to get it in a pure form is a big challenge. So here I've shown just one examples with different process. So if we look at a realistic picture how MOF looks like, so let's go into this. So this is the synthesis. This is the crystals we got after synthesis of HKUST1. So it's a blue, very nice crystal. So when we lower its dimension, so let's move and let's zoom in into its structure. So we go into a nanometer scale. We find that they have all repetitive units, high long range ordering, and at the unit cell level you see that they have highly porous structures in all the places. So this is more like a spongy system. So that is why the properties is what is very important for this metal organic framework. And because of all these kinds of properties, it's what do you say, its popularity is very high. So the basic idea is it is highly crystalline, the property wise. So you have already seen this video where they have a long range ordering. So that means each and every centers, each and every repetitive units are exactly same. It has very less defects. And the second one is high surface area. And the tunable properties means, see, the basic unit is a metal and a ligand. So now you can have different kinds of ligands. You can have different kinds of metals. So the permutation combination can become almost infinite. And the last one, that which is very important for any preparation or manipulation of any functional materials, is the stability. So stability wise, chemical stability, thermal stability, all are extremely superb. So to give you a brief perspective idea, so let's say HKUST1. So these yellow centers are all pores, vacant places. So I have designated it with space. So this is where all your guest molecules can come and adsorb. So the surface area for HKUST1 that I have shown about the synthesis is 692 meters square per gram. So this is very high. Meter square per gram. That means 1 gram of this material is going to have around 692 meters square of surface area. Similarly, the highest one reported till date is NU 110, which has a surface area of around 7,140 meters square per gram. This is very high. So perspective wise, if I show you a soccer field whose surface area is actually 7,000 meters square, that means if you take 1 gram of that NU 110, let's say it must be like this much amount. So the surface area will be almost equal to around almost a soccer field. So that means it is highly porous. So whenever any material is highly porous, we can always think of a lot of properties like the absorption properties, the separation properties. So all this comes into play for its role as functional materials. The second one is the tunability. Now, where are the changes that you can do so that you can manufacture or synthesize more and more tunable functional materials? Like you can have metal node tunability, that for example, this is the metal that you're using. You can change any metals, and depending on the types of metals, you can change the properties. The ligand tunability, you can have any kinds of ligands here, whether you have some nitrogen containing ligand or sulfur containing ligands. You have a huge array of possibilities of changing it. So this is known as privileged metals tunability, because when you make a metal organic framework, you can always have more than one metal ion. So that way, if you have, for example, 2 metal ions, so this metal ion will behave in a different way, and this metal ion will behave in a different way. That means you can again bring some tunability. And at the same time, the last one that I would like to say is the multifunctional tunability, where you can add different kinds of functionals to increase different kinds of properties. Now the other properties that is important is the stability. So here again, this is what we have done in our laboratory also. So this is the chemical stability that we are showing. So what we did was we synthesized SKUST1 and we removed the apical water molecules that it contains. So once we remove the water molecules, that we can easily categorize by different analytical tools. So it changes color. See, this is turquoise and this is almost dark blue. But if we look at the powder XRD, we see that almost both the structures are almost stable. And yes, this process is highly reversible. So it again comes back, and this structure will become again into the unactivated form. So again, if you even with this is copper 2 ion. So the copper 2 ion, if we reduce it completely to copper 1 ion, and still we see that the structures are almost stable. So it has, I haven't shown the structural stability part. So I will directly go into the spore controlled functional materials. So what happens is, because it has a spongy type of nature, so these sponges can actually act for storing and separating different molecules. So here you add a lot of functions, and it can be used for different kinds of applications like methane storage, carbon dioxide separation, hydrogen storage, catalysis, enantiomer separations, everything. So I'll give you just brief few examples because we are short of time. So for example, this is UTSA 76. UTSA 76 stands for University of Texas at San Antonio. So it has almost the highest reported methane storage capability. And so if we look at this graph, there's this line, this dotted line represents just compressed methane gas in a normal tank, and this is with UTSA 76. That means huge methane storage can be applied. So I'll skip this slide. This is also about methane storage. So carbon dioxide storage, it is also, NU 110 is also highly used for carbon dioxide storage. So we have this carbon dioxide sequestering process, so that can be there we can use this materials. So NU 110 actually absorbs around 38.5 weight% at 1 atmosphere. So this is very high. 38.5 weight% is a very high amount. So you can just it can be used for removal of carbon dioxide. Similarly, hydrogen storage is also a very hot topic. We need hydrogen for hydrogen fuel cells or hydrogen fueled cars. So till that, this MOF5 is one of this material. MOF is known as MOF5. It's highly sorted out, and they have around 7.1 weight% at 40 bars. So yes, it needs to be improved, but still these numbers are relatively very high. So the final one in this pore controlled functionality is the separation of C2H2 and C2H for the acetylene and ethylene part. So this material, which is a copper containing metal organic framework, it selectively separates this C2H2 and C2H4, and this is the highest reported one. So let's move on to the other kinds of functional materials, which is generally I've classified it as engineering based functional MOFs. Here, this is more about a post-synthetically modified metal organic framework. So once a metal organic framework is prepared, so what we do is we add lots of functionality, we add lots of materials like some dyes. So depending on what attributes we know, because our MOFs are highly porous, so we can these MOFs can act as a host or a storing or what you say encapsulating agents. So I'm not going to highlight all of this. I'll just give you a few brief examples and straight away move into what we do in our labs. So this is an example of white light emitting material. So this is a metal organic framework, Day2 28, where phosphor material dye is encapsulated into its surface, and what we get is a white emitting LEDs. Similarly, we have other luminescent based MOF. Here, ZZU88. In ZZU88, perylene, which is already known as a very high fluorescent material, is encapsulated, and it actually it shows a very linear dependence of this 473 and 615 nanometer absorption bands, emission bands. So 473 is for this perylene molecule, and 615 is for the metal organic framework. So we see that there is a direct correlation, very linear correlation between the emission decrease of this 473 and emission increase of 615, which actually acts as which can be used as a ratiometric thermometers, because the temperature dependence changes is almost linear. So which can actually record how the temperature is changing. So all these devices have been made. So the final one that about its properties is oxygen sensors, which is also very good. So here, there's indium-based MOF. In indium-based MOF, this terbium-3 ions is attached, is encapsulated, and the change in the quenching of this terbium emission when exposed to oxygen has been recorded. So this actually gives rise to a very good oxygen sensor. So there are lots of possibilities with metal organic framework and lots of different functionals. So I will straight away move into what we are doing. So the work that I'll be presenting from now on will be mostly done by Sagar, Debesh, and Khanindram. So Shivanand and Deshat has recently joined, and they are working in my crew. So I'll start with mostly the first one is pore controls reactivity. So this is the work we have done. What we did was we started with the same ligand and same metal ion, and what we did was we synthesized, we made different kinds of pores here. So here it looks like more like a hexagonal. It falls in the hexagonal crystal system, so it has a hexagonal pores. And whereas, yes sir.
5 more minutes to wind up.
Yeah.
5 more minutes to wind up.
Okay, father. Okay, father. And the second one is a tetragonal form. So both the structures comes from the atomic constituents are almost similar, but the pore, how the pores are oriented are completely different. So what we found in this case is for simple reactions like opening of this epoxide ring with an nucleophile, we found that with tetragonal system, we find both the cis and the trans product, whereas for hexagonal system, we have absolutely selective trans oriented products. So this is something, this is highly chemoselective, and this chemoselectivity is completely coming from the pores. So it's the functionality of the pores that we have introduced. Now the second example that we'll be showing is the multimodal catalytic attributes that is actually instituted by this metal organic framework. So we synthesized again the same HKUST1. So I already told you about how the coordination of this coppers, let's say this is copper, this copper center generally have water molecules, and it looks like a turquoise, and this can be removed easily by activation. So we can remove it by applying strong vacuum and high temperature, and they go out and we get a blue colored material. So the surface area also drastically changes. For the unactivated turquoise one, we have a surface area around 836 meters square per gram, and whereas the activated one has around almost double the surface area. So now while changing into these two forms, what we could understand, where we used this system is we designed some reactions. Like for example, we have an alkene system here where we can introduce a nitrogen here and make azidirenes, cyclic nitrogen cycle compounds, right? So this reaction can only be catalyzed by the activated one, means the copper ion which is devoid of water. Whereas there is other reactions where this nitrogen cycle is removed by a nucleophile and you have a ring opening product. So this reaction can be done by either any of this two activated or unactivated metal organic framework. So that when we couple these two reactions from here to here, then we can actually create a switching between uh, these two forms, which is activated and unactivated. So once we turn on the unactivated one, we get this product, and when we turn on the activated one, then we get the agitated product. So in this way, by using a simple uh, formulations or simple functional modifications, we could actually form both CC, CN, CS, and CO bonds containing compounds, so which is again of high use. Now the last examples that I'll be showing is we have derived some composites, metal composites from MOF that we have prepared and use them as electroactive material. So what we did was we synthesized some one-dimensional 1D compounds containing nickel, and we converted them into composites. So we converted this nickel 1D into at high temperature and formed a nickel carbon composites, which actually contains 50% nickel carbides and 50% metallic nickel. Now this composite is modified into an electrode. So we use we coated this material over a glassy carbon electrode, and we formed an electrode of this nickel composite material and did some electrochemical reaction. Now the electrochemical reaction that we chose was specifically oxygen reduction reaction and oxygen evolution reactions. We know that in fuel cells, both these oxygen reaction processes are very important. So we found that our material that we have prepared is a very stable one and forms a very good oxygen reduction process, and at the same time oxygen evolution process. So this material actually acts both as a bifunctional material where both oxygen reduction as well as oxygen evolution process are done. So with this, I will stop, and I would like to acknowledge the definitely Cushing College and St. Joseph College, Sikkim University for all the facilities that we have, Missouri SNT for my initial work on metal organic framework, and SORB DST and DST Inspire for funding my research. And I would be glad to take up questions if you have any. Thank you. Thank you very much.
Excuse me, sir.
Okay, thank you, Anand. Due to shortage of time, we will not be able to take up the many questions. So
Yes,
I just one question from one audience to Anand.
yeah, we have one
Question please from any one of the audience.
So we have one question from Ghulam Martaza from Pakistan.
Okay.
I think he will ask you the question.
Please go ahead.
Ghulam? I think he's not available now. We can skip to next question.
Hello, can I ask a question?
Yeah, sure. Go on.
Yeah, so you said something like active matter, active particles or something like that. What do you mean by active particle?
Active? What is it?
You said something like in one of the last slides, you said active material or something like that. What do you mean by active material?
I mean electroactive materials. I think I said
Those, okay.
electroactive materials. So this carbide, this composites, this nickel metal composites, these are being derived from a metal organic framework. So what properties it acquires from metal organic framework is that because metal organic frameworks are porous, it attains that porosity, number one. And number two, in this carbides, actually the carbons that has been formed over the surface of this nickel are very evenly distributed and they are highly conducting. So because they are conducting, you have a metal ion and they are porous, we modify them as electrodes because it's conducting. So that's why we are using it as an electroactive materials.
I see. Thank you. Actually, active material in physics has a different meaning. That's why I was wondering if you are doing similar kind of things. Thank you.
Okay, thank you.
Yeah, sir. Excuse me, sir. Hello. Hello.
Yeah.
Yeah, you have shown that the carbon dioxide storage and hydrogen storage.
Yeah.
Using metal organic.
Yes.
So in this particular work, what kind of material?
Yeah. Go on.
Can I ask?
Yeah, go on. What kind of material you were saying?
Yeah, what kind of material you have used in carbon dioxide and hydrogen storage?
Okay, so mostly for carbon dioxide storage, see, the porosity, number one, is very important, but the interaction with nitrogen groups and metal ions, the selectivity of metal ions are very important. Like for hydrogen, it has always been seen that if you have aluminum, indium, so these are very active hydrogen interacting metals.
Okay.
So the basic chemistry is same. What we are using is we are just adding the added functionality of porosity into the main main properties. Okay, so especially carbon dioxide. So if you see carbon dioxides, lots of copper containing metal ions are used. So copper are mostly seen as very active, carbon dioxide interacting metal ion in metal organic framework with that porosity.
So sir, is it depends on the polarity of the reactant and the absorber?
Definitely. Polarity, there are lots of things. See, the basic idea is you should not have any metal ion which strongly adsorbs, or you should not have any metal ion which loosely adsorbs. Because the reason is, see, if you are absorbing hydrogen ion, you have to dissolve it as well, right? So if your material is absorbing carbon dioxide, it should be physically dissolved also. So the balance has to be very important. So it should not be strongly interacting, it should not be weakly interacting. Rather, the interaction had to be very much controlled, very much balanced. So that is only how we are going to get a good material which can be used for storage or separation, for storage for any kinds of gases or any kinds of ions or molecules.
Thank you, sir.
Sir, I have a question. May I ask?
Yeah, go on. Hello.
Thank you for providing such a great opportunity. Yes, I'm audible, sir.
Yeah. Go on.
Thanks, Dr. Anij. I have learned a lot from your expertise and valuable remarks about metal organic framework. Sir, I am from Pakistan. I have two questions.
Yeah.
What about tools that you have used for characterization in MOF? And secondly, which ligands and metal that you have used for synthesis? You have made ligands by yourself?
Okay, I couldn't get the second question properly. Let me answer the first one first. For characterization of metal organic framework, the
I would
basic.
like to ask you
Yeah. What was the second question?
Which ligands?
Oh, ligands.
And metal that you have used for synthesis? Yeah, ligands. And
I got it. So,
this link occurs.
So to characterize any metal organic framework, the basic tool that you need is, the first thing you need is you need a good single crystal X-ray diffraction machine. So because once you identify all the structures, then a lot of things will become easier. So single crystal X-ray diffraction, powder crystal X-ray diffraction, these two things are very important. You need a surface area analyzer to know the surface area. You need to have normal IR spectrometer. I would say TGA would be very helpful. TGA to start with. To know the oxidation state properly, XPS would be very helpful. Yes, if you have a magnetic material, you can always go with squid magnetic analysis with other susceptibility measurement devices. And what else?
And sir, what about second question?
Yeah, second, the metal line that I'm working with is, I work mostly with the first row transition metal line. Okay,
right.
So the first row transition metal line generally are highly sorted out. Number one, because of the easy availability, the price, and the chemistry as well. Okay, so you can do a lot of things. They have variable they can have several variable oxidation state. They can exist in different kinds of structures. They can form different kinds of interactions. The coordination numbers can be variable. So you have more and more parameter to work with. And regarding the ligands, I mostly work with carboxylated, polydentate carboxylate type ligands and nitrogen containing ligands, because nitrogen generally have a very strong interactions for specific reactions like oxygen reduction reaction, many electroactive reactions. So I generally work with carboxylates, polycarboxylates, and polynitrogen containing ligands.
Sir, I got it. Thank you for your expertise and valuable remarks.
Hello. Hello.
Yeah, Father.
Hello. Thank you very much. And participants, whoever has questions, you can directly mail to Dr. Anand and get your clarification. Is it okay?
Yeah.
So it's time to conclude. Gratitude is the language of heart. We are very grateful to Professor Indrajit Sharma, Dr. Devasis Bora, and Dr. Anand Pariyar for sharing their knowledge with all, and united all of us, the mind of all of us, especially the young one and the researchers. Thanks a lot to all the speakers and all the participants for their patient hearing. Thank you. Over to Dr. Amit.
Father, we are really pleased to have you here in this session. Thank you very much for nicely coordinating this session and giving a very beautiful, wonderful uh, introduction of our respected speakers. And once again, I would like to thank the speakers for your sharing your work to our participants, and hope that the participants will contact you by the time, inspired from your work and regarding the confusion if they have with your work. Okay, thank you very much. And one small announcement to the participants. Now we are going for the oral presentation, and like yesterday, we have got parallel session for this oral presentations also. And the room one will be this session that is going on, and the room two, there will be the different room. And I have already shared the link in the WhatsApp group, as well as here in the chat also, you can see there. And regarding the participants in the room one, that is session going on here, we have the speakers, Ms. Bhinduja P from University of Calicut, who will be discussing about the mathematical modeling in silicon anti-cancer studies of phytochemical cosmestrol, and the Ms. Pragya Singh from IIT BHU, and who will be discussing on organic and inorganic materials. And similarly, the next speaker is Mr. Dwayanidhi Tatkuli from Tribhuvan University, who will talk about the astrophysics. Now, similarly in room two, that is the next room, we have the speakers, Dr. Ambika Pradhan from SR University Sikkim, who will discuss about the soft condensed matter, and followed by Mr. Sunny Nandi, who he will share his work on energy materials, followed by Dr. N. Shivasankara Reddy, who will also discuss about the energy materials. So participants, you have the choice, so which room to join. You can stick to this room one, or you can shift to the room two. And once the session in room two is over, you can again come back to our session. This session will continue to the valedictory session. And for that, you can use the similar link that you have joined using that link this session. Okay, fine. Thank you very much. And with this, we are heading for the oral presentation. And for this, I would like to request our Professor V. Madhurima from Central University of Tamil Nadu to kindly chair the oral presentation session. Kindly, ma'am.
Good morning, everybody. It's a pleasure to be back, and I'm here on substituting Professor Ankit Hapa because of some connectivity issues. Let's straight away get down to the oral presentations. Each speaker gets 8 minutes and 2 minutes for questions. I request all speakers to kindly adhere to the time. The first speaker for this session is Ms. Bhinduja from University of Calicut, and the title of her talk is In Silico Anti-Cancer Studies on Phytochemical Chemistry. Bhinduja. Are you here?
I think she is not here. I think she's not there. I can't find her.
Okay, let's then just move on to the next speaker and see if she will be back. Is Pragya Singh here?
Pragya Singh, she is here.
Yes. So, are we ready to go?
Yes, ma'am.
Oh, wonderful. So let's start with Pragya Singh, who's a research scholar at the IIT BHU. And she will be speaking on pressure-dependent structural phase transition studies of bismuth ferrite doped lead titanium solid solution systems, BiFeO3 doped PBTiO3. Pragya Singh.
Hello.
We can hear you.
Okay, thank you, ma'am. Good morning, everyone. My name is Pragya Singh. I am a research scholar at School of Material Science and Technology, IIT BHU. Today, I am going to give an oral presentation based on my research work, that is pressure-dependent structural phase transition studies on bismuth ferrite doped lead titanate solid solution system. Just a minute, I'm trying to share my screen. Is my screen visible?
No, we can see you. But on two screens. I mean, I can see you on.
Yeah. Now, is it visible?
Yes, please go ahead.
Okay, so my presentation is based on one basic introduction and what are the objectives of my work and how I have synthesized the samples and how the data has been collected and the results and discussions. So perovskites, they are very popular materials in area of material science because of the fascinating variety of phase transitions exhibited by them. They are basically ABX3 type of materials, and when that X atom is oxygen, then they are called perovskite oxides. They are believed to be of the parent group PM bar 3M, that is cubic. Basically, the structural phase transition in perovskites are of two types. First is ferrodistortive and second is anti-ferrodistortive. Ferrodistortive occurs because of the instability of the zone center optical phonon mode of the Brillouin zone, and the anti-ferrodistortive phase transition. This occurs because of instability of zone boundary optical phonon modes of the Brillouin zone. In ferrodistortive, we have the same number of formula units in parent as well as product phase, while in case of anti-ferrodistortive phase transition, the product phase, it has multiple number of formula units with respect to the parent phase. Now talking about lead titanate. Lead titanate is a very popular classic ferroelectric material. At room temperature, it has a tetragonal 34 mm space group like crystal structure, and because of this huge tetragonality, it is very popular because it is the end member of one of the most popular commercial piezoelectric compositions. It has very high spontaneous polarization, which has been calculated at 86 microcoulomb per centimeter square. Now, if we see the phonon dispersion curves for lead titanate, here we can see that it has very strong zone center for optical phonon instability. At the same time, it also has weak zone boundary phonon mode instability. Here we can see. But this P4M phase, it is obtained by directly as a result of instability of only zone center optical phonon mode. So, talking about the high pressure behavior of lead titanate, there is a very classic study by Samara et al. In which he has studied a number of classic ferroelectric materials, in which he has found that the ferroelectric transitions are suppressed at high pressures, whereas AFD transitions are favored at high pressures. So he categorized lead titanate in the ferroelectric materials, and its phase and its polarization was found to be decreasing with increasing pressure. There is a study by Names et al. They have found that the lattice parameter, they show anomalous behavior with increasing pressure, where the C parameter decreases with increasing pressure, while the A parameter first increases and then decreases with increasing pressure. Now, talking about recent studies, the high pressure behavior of lead titanate is highly controversial because there are two different propositions which are entirely different. First picture says that with increasing pressure, there happens a morphotropic phase boundary, which is commonly known as MPB, like phase transition from tetragonal to monoclinic phase, associated with a rotation of the ferroelectric polarization vector. That second picture, it says that there is no such thing like polarization rotation. Rather, with increasing pressure, we get a AFD type phase transition, in which after a critical pressure, we get a reentrant ferroelectric phase. Now, what is MPB? Those who are not familiar with this, in the composition temperature phase diagram, we have this vertical line in which for a broad range of temperature, just by changing the composition, we get the structural phase transition. This is known as MPB or morphotropic phase boundary. Now, AFD transitions, they occur because of the rotation of this oxygen octahedra. And because of this oxygen octahedra rotation, the unit cell gets multiplied and we get superlattice peaks as a result in the diffraction patterns. When we talk about recent theoretical studies, now there is a group which has presented the MPB-like picture. they say that the tetragonal p/mm phase, it transforms to monoclinic and then rhombohedral and cubic like phase with increasing pressure, which supports the polarization rotation. And the second picture, which is by the group of Cornave, they say that the tetragonal p/mm phase, it transforms to I4CM, which involves the AFD transition, in which first the ferroelectricity decreases and and then above critical pressure it increases with an intermediate non-ferroelectric like phase. Now, there are a few more studies. The third study is by Franti et al., which says that the p/mm phase transforms to R3C and then R3C space groups, which involve AFD type transition, but there is no MPV like transition to monoclinic phases. There is another particular study by Ganesh and Cohen. They have again confirmed the finding of this Wu and Cohen, only this cubic-like phase. This has been replaced by R3C or R3C space group. Talking about experimental pictures, the two pictures which I have talked already, they have their own experimental support. The first group presents experimental study in support of their theoretical picture like tetragonal to monoclinic to rhombohedral, whereas the hello?
Pragna, you have 2 more minutes.
Okay, and the second picture presents confirmation about the AFD picture. Now there are many questions which arise like what is the exact nature of transition, AFD or MPV? So to address this issue, we have selected the bismuth ferrite of lead-ignited solid solution system because bismuth ferrite has a strong zone boundary optical phonon stability, so it will enhance the intensity of any superlattice peaks if there are any superlattice peaks present. So the data has been collected at Petra 3 extreme conditions beamline. This is the room temperature XRD pattern which shows a clear single P4M space group phase, and this is the comparison by high resolution and extreme condition beamline. Here we can see the evolution of peaks. Here we can see the nice splitting of tetragonal structures. And we can see that in this graph, where this singlet peak, this is now a doublet peak, which gives a clear signature of the structural phase transitions. Now between 5 to 7, there is almost cubic-like singlet appearance, and above this pressure, here we can see that there is again splitting in this peak. So, and the best feature was that at the same pressure, 2.15 gigapascal, we observed clear, nice superlattice reflections, which was direct evidence of a AFD phase transition. So this P4M phase was observed by decreasing pressure also, so it is completely reversible structural phase transition. And we analyzed the 2-2-0 and 2-2-2 peaks by peak deconvolution, and which supports that it is not rhombohedral, because for rhombohedral 2-2-2 and 2-2-0 should be doublets, but they were found to be triplets and quadruplets. Now, to again confirm this by refinement, we incorporated the possible space groups which can be observed because of zone central and zone boundary optical phonon modes. These were the possibilities. So except right clinic, we tried all these space groups and we found that the monoclinic CC group gives the best fit, which involves the polarization rotation as well as AFD transition. It kinds of combine all the pictures. Just a minute, ma'am. Now we have plotted the equation of state and variation of lattice parameters. Here we can see that from P4M to CC phase, there is a clear first order phase transition, and at the point at which the 2-2-2 profile, peak profile gets reversed, here there is a peak signature, which is not here in linear pressure, but when we plot log of pressure, here we can see that there is a departure from linearity. Talking about lattice parameters, we can see that the C and A parameter, they get reversed above this 7 gigapascal. This zoom picture gives the more clear picture, and the best way to view this transition is through monoclinic angle, which shows first a constant decrease and then increase. Now, to check the polarization,
you have to wind up. It's you have short past your time.
Okay, ma'am. So this polarization we found first decreasing, and then it shows sharp increase, just like at MPB we observed most commonly, and in this case polarization decreases with increasing pressure as expected, but above this 7 gigapascal we observe a constant increase in the polarization, which confirms the trend ferroelectric phase. And when we plot the tilt angle, we see that in this increasing ferroelectric phase, this tilt angle starts increasing very abruptly, which shows that this tilting is providing the required mechanism to accommodate the increasing volume and also to accommodate the increasing polarization. So this is the first experimental proof which which shows that with increasing pressure, there is no only MPV or only AFD like picture. We have a combination of both, and which was missing in previous studies. And these are the references. Thank you.
Thank you, Pragya. I can see that it's been a very extensive work, but the allotted time was only 8 minutes, so there was a problem. Are there any questions for the speaker? Because the work was extremely interesting. Do we have any questions for the speaker? No. So, Pragya, you had discussed about the controversies regarding the perovskite work in one of your slides.
Yes, ma'am. Yes,
how does your experiment resolve the controversy?
Ma'am, the first picture is MPV light phase transition. It means from tetragonal phase of lead titanate, it transforms to monoclinic phase, which permits the rotation of ferroelectric polarization. While second picture, it says that tetragonal phase goes to I4CM phase, which involves only AFD transition. There is no MPV like polarization rotation possible in this space loop. But for this I4CM space group, it should have a clear superlattice peak if there is any AFD transition involved. But the experimental studies, they don't have any clear picture. Like if there is AFD transition, then there should be clear superlattice peaks. Like here in this experimental picture, they are saying that that above 20 gigapascal I4 by MCM and I4CM phases should be there, but there is no clear superlattice peaks below 43 gigapascal. So in our study, here you can see, here we have observed clear superlattice peaks, 3 by 2, 1 by 2, 1 by 2, 3 by 2, 3 by 2, 1 by 2, 3 by 2, 3 by 2, 3 by 2. At this same pressure at which we get the structural transition here. Like in tetragonal phase, we have singular.
That's fine. I mean, I think I get the picture. I just wanted a short answer. Thank you. Any other question quickly? Any short question?
Ma'am, which type of XRD are used?
Sorry?
Which type of XRD? The temperature dependent. Temperature dependent.
At ambient temperature, pressure dependent. From Petra 3, there is beamline P02.2, which is called extreme conditions.
Unit cell volume calculated from XRD?
Sorry, unit cell volume?
You are calculated from XRD or any other calculation technique?
By linear refinement, you get the lattice parameters as well as unit cell volume. Here I have shown.
I think for the it's completely overshot the time. So any other questions, kindly take up with the speaker either on the chat or through an email. Thank you, Dr. Pragya Singh, for a good presentation. Let's move on to the next speaker. The next speaker is Mr. Dayanidhi Chatkuli from Tribhuvan University in Nepal. And he'll be speaking on a spectroscopic study of the low redshift dwarf galaxy SDSS J134326, etc., to calculate star formation rate. Over to you.
Thank you. Is my slide visible?
Yes. Please go ahead.
Okay. First of all, I would like to thank the organizers, the Corsen College, the St. Joseph College, the Condensed Matter Physics Research Center, Actually, this is our combined work. Myself, Dayanidhi Chhatkuli, my co-supervisor Sanjay Podel, and my supervisor Professor Binil Aryal. The title of my talk is Spectroscopic Study of the Low Redshift Dwarf Galaxy, STSS J13432.6.99 plus 43111 8.7 to calculate star formation rate. This is my outline. Motivation. A galaxy with low metallicity, low surface brightness, low luminosity is commonly known as a dwarf galaxy. If the gravitational field of the dwarf galaxies interact with each other and produce disturbances in their morphological and chemical properties, dynamical properties, then the galaxies are said to be interacting dwarf galaxies. I have shown a sample of interacting dwarf galaxy system, NGC 2604. Here we can see two different dwarf galaxies which are interacting. This is another sample of dwarf galaxy, NGC 3169 and NGC 3166. According to lambda cold dark matter cosmology, dwarf galaxies are considered to be the first formed dark matter dominated objects, which are considered to be the building blocks of the universe. Therefore, their studies provides the knowledge of early process of structure formation. How various morphological dwarf galaxies come to exist and whether they are transformed from each other during the course of evolution is an important question. There are many interacting dwarf galaxies whose evolution by their merging history is yet to be explored in detail. Methodology, object of interest. We compiled something technical mistake. We compiled, we selected a dwarf galaxy of our interest from the catalog compiled by Podel et al. 2018. This is our selected galaxy, dwarf galaxy of our interest. Here we can see the main body, central body part of the galaxy, which is shown by cross mark. This is blue in color, significantly blue, and we can see the extended arc-like tail structure of the galaxy, which is at the 5 kiloparsec distance from the main body. This is the galaxy which is just formed after interaction. And in right panel of the diagram, I have shown a spectral spectra of the galaxy. We can see many emission spectral lines of the galaxy. The emission lines are due to N1, H alpha, H beta, H gamma, O3, etc. Methodology, method. We have downloaded the SPSS archival data using Aladdin. Then the data was plotted by using a software origin of 18th version spectra of the galaxy. And the peaks in the emission lines were identified and fits. Okay. Then finally, using the area of the Gaussian fit of H alpha line, we calculated star formation rate of the galaxy using the empirical formula proposed by Kennicott. Gaussian fits, we have shown a sample of Gaussian fits. Only 4 samples are shown which lie in Balmer series. Here we can see red color a solid line curve that represents Gaussian fit. The broadening of the line is mainly due to Doppler's broadening. Results and discussion. This is a table which enlists the Gaussian parameters of the 8 selected Gaussian fits. We have selected only 8 curves out of 20 curves we have selected. Then it is based on the strongest line, higher value of intensity. Here we can see the red mark values. The strongest line is obtained due to O3, and second strongest line is due to H alpha, and weakest line is due to N3. Likewise, the area and height are also changing accordingly. In the last column, we can see the value of coefficient of regression is almost 100%. It means that observed data is in almost perfect agreement with the Gaussian distribution. Similarly, in second last column, we can see the negative values of offset corresponding to HE1, H delta, O3, and H alpha. This means that the tail in the Gaussian curve in left-hand side is longer than that in right-hand side. Likewise, we can see the positive values of offset corresponding to S gamma, S beta, and N2. This means that the tail in right-hand side of the Gaussian curve is longer than that in left-hand side. Another result is a scaling relation. It was done by Lee et al. In 2009 for star forming normal galaxies. In left-hand panel of the diagram, we can see gray color dots. This represents the star forming normal galaxies. This is a relation between metallicity and magnitude. And this deep black color is our galaxy of interest. It shows that our galaxy of interest is outlier. That means it has low metallicity. Likewise, in right panel, we can see a relation between star formation and magnitude. Here also, our galaxy of interest lies outside from the mainstream of the star forming normal galaxies. That means our galaxy of interest has a higher rate of star formation, but it doesn't follow a scaling relation. Star formation, we calculate star formation rate, which is found to be 0.019 solar mass time per year. The line ratio of S alpha and S beta is found to be 2.73. This implies that the galaxy is nearly dust-free and star forming. The line ratio of N2 and S alpha is found to be 0.011. Using this value, we calculated metallicity of the emission line of the spectra, which is found to be 7.85 dex. We conclude that we have presented the formation of the galaxy of our interest as another evidence of forming blue compact dwarf type galaxy through the merger. Finally, I would like to acknowledge Sloan Digital Sky Survey STSS, from where I downloaded the data. My University Grants Commission of Nepal are awarding by PhD fellowship. Thank you.
That was a very crisp and very good talk, if I might say so. Are there any questions for the speaker?
Yes, ma'am, I have a question.
Yeah, please go ahead.
Okay, so may I ask you a question?
Yes, please.
Yeah, please go ahead.
So since you were talking about galaxies and dark energy, what can dark galaxies tell us about dark matter? Are they related?
Yeah, related. It is believed, according to lambda CDM model, that dwarf galaxy is supported by dark energy. To form star, there will be higher rate of star formation, especially in field environments.
Okay, we are really running short on time, so I would request for all other questions to be taken offline, either in the chat or through the email, because I think we need to, we have the third speaker who's come in. So thank you very much, Mr. Dayanidhi, and let's move on to the last speaker of the session, who is from University of Calicut, and she'll be speaking on in silico anti-cancer studies on phytochemical cholesterol. Vinduja, please start your presentation and kindly stick to the timing of 8 minutes.
Okay. So is it visible?
Yes, it is. Please go ahead.
Okay. So good morning all. I am Vinduja from University of Calicut, Department of Chemistry, and I am doing my research under the guidance of Dr. K. Muralidharan. And today I am going to present a very small portion of my research work entitled In Silico Anti-Cancer Studies on the Phytochemical called cholesterol. And the work is purely based on the technique molecular docking. And before going to the detailing of our research work, let me give you a brief introduction to the concept of molecular docking. And molecular docking is an attractive scaffold for understanding the drug biomolecular interaction for rational drug design and discovery. And it is a kind of bioinformatic modeling which involves the interaction between two molecules to form a stable adduct. And depending upon the biomolecular interactions, it will give three-dimensional images of all the possible complexes it can be formed. And docking simulations predict optimized docked conformer depending upon the total energy of the system. So it gives insight into the preferred orientation of a ligand within the active site of the target to form a stable complex. Simply speaking, it's a kind of lock and key mechanism in which target can be considered as a lock and ligand can be considered as key. And when this two comes together in a proper manner, a stable structure is formed. Similar in the case of protein. And protein, there will be an active site and the ligand bind to the active site in a very proper manner to form a stable protein ligand complex. In our study, we are mainly aimed at anti-cancer studies. So, medically, cancer is known as malignant neoplasm, and it is a term used to describe a large group of diseases that are characterized by a cellular malfunction. Or otherwise, we can say that uncontrolled multiplication of abnormal cells result in cancer. There are several types of cancers reported so far, and hence the area of chemotherapy is still enlarging. There comes the relevance of anti-cancer drugs. Anti-cancer drugs are used to treat malignancies or cancerous growth, and it may include antimetabolites, hormones, natural products, etc. Please note that natural products have the potential to act as a chemotherapeutic agent. So in our study, we selected cancer-causing kinase protein as a target protein, and the human genome encountered 538 genome protein protein kinases that transfer gamma phosphate group from ATP to serine, threonine, or tyrosine residues. So most of the protein kinases promote cell proliferation, survival, and migration, and they are also associated with the oncogenesis. So kinase inhibitors play a prominent role in the treatment of cancer. So here we are selected mainly 3 kinase proteins for our work: BRAF, JAK3, and MEK1. So this is some description about the selected proteins, from which we can say that they are involved in multi types of cancers, including lung adenocarcinoma, pancreatic cancer, etc. And the molecule under study is cowmestrol, and cowmestrol is a phytochemical which belongs to the family of coumestin, which show a large number of bioactivities like neuroprotective, anti-aging, antioxidant, and anti-cancer. They are widely distributed in spinach, pea, soya, alfalfa, ladino, clover, etc. And objective of this work is it's purely based on molecular docking-based reactional drug design, which involve the identification of binding modes, prediction of binding affinity, and studies on protein ligand interactions. So let's have a look how to perform this docking. Actually, the 3-dimensional structure of the cowmestrol is downloaded from a software called PubChem database in SDF format, and it is then converted into PDB format using Open Bubble application, and later it is converted into PDB-QT using Autodock tools. Similar manner, 3-dimensional images of proteins are downloaded from protein data bank in PDB format. It's also converted into PDB-QT. So after that, molecular docking was performed using Autodock Vina tool, and the 2-dimensional as well as 3-dimensional interactions are viewed using Discovery Studio application. Coming to the docking result, from the table, it is clear that the cowmestrol show a strong binding energy with all the selected target, and it show minus 9.3 kilocalorie per mole binding energy with the BRAF, and minus 9.5 with the JAK3, and minus 9.1 kilocalorie per mole with the MEK1. Just comparing the binding energy values of inbuilt ligands, with the BRAF, it shows minus 8.6, JAK3 minus 8.1, MEK1 minus 7.7. And the lower binding energy indicates higher inhibition potential with the selected target, and in all the 3 cases, the inhibition potential of cowmestrol is much higher than that of inbuilt ligand. These are some representation of 2-dimensional and 3-dimensional interaction of cowmestrol within the active site of JAK3. Here we selected the protein with the PDB ID 4HBD, and here it is clear that a strong conventional hydrogen bond is observed with the leucine 905 with the OH group present in our molecule, and several other interactions are also observed. And this is interaction with the MEC1, and it is, sorry, BRAF. And here also you can see a strong conventional hydrogen bonding interaction with the cysteine 532. And this is the interaction of our molecule with MEC1, and here also you can see conventional hydrogen bonding interaction with the cysteine 207, aspartic acid 152, and histidine 145. And from all these studies, it's clear that our molecule is well interacted with the surrounding amino acid residues present in the protein targets. So let's have a conclusion. The use of herbal drugs has evolved as an alternative, safe, low-cost and convenient method for cancer therapy. And the phytochemical cowmestrol can be considered as an efficient inhibitor of cancer-causing kinases. Cowmestrol showed good interaction with all the three targets, with the binding energy values being -9.5, -9.3 and -9.1 kilocalorie per mole respectively with the JAK3, BRAF and MEC1. More interestingly, this binding affinity of cowmestrol with all the target was even higher than that of the corresponding inbuilt ligand. So, cowmestrol can act as a potent anti-cancer drug against various types of cancers. Thank you. Stay safe and stay home.
Thank you, Induja. That was a crisp talk again and very effective. Are there any questions for the speaker? Okay, in case there's nobody asking, I have a question. When you have taken the original structure for cholesterol from, you said
PubChem database, ma'am.
PubChem database.
Yeah.
Have you done a structural optimization?
Yeah,
Before
sure.
you started the document?
Yeah.
So what procedure?
DFT calculation.
At what level? Like what basis?
631G plus 2D2P.
And how many conformers have you tried for docking? Because that's one of the major issues.
Right? Yeah, 10 conformers we selected, and among which the lowest energy conformer was selected for docking analysis.
It would have been nice if you had given us the conformer to get a visual cue for what has been done.
Okay, actually, in the case of auto docking, Autodoc Vina, actually we used the Autodoc Vina, in which they also calculate. We not need for DFT calculation. It also itself calculate the lowest conformer and bind. That's why I did not put the DFT studies.
But it would be nice to get a visual idea of what the conformer is. But I understand what you're saying. Are there any other questions? Okay, in case there are no questions right now, let us thank the speaker. In fact, let me thank all the three speakers for a nice presentation. And especially the two of them who stuck to the time and have saved a lot of our time here. Thank you very much, and I think we'll be heading for a 5-minute break. Is that right, Amit?
Yes, ma'am. 5 minutes break.
Yes. So let's go in for a 5-minute break and reassemble back in 5 minutes. Thank you, everyone.
Yeah, this session will continue. You can just have to come and join.
Yes.
The link will be the same.
Patient training.